I'd like to introduce Dr. Richard Norte. He is a faculty member at Delft University of Technology in the Netherlands. His lab focuses on novel techniques for designing, fabricate, and measuring nanotechnologies which meet the stringent requirements for quantum hardware based on optics and mechanics. He holds a double Bachelor of Science degree in physics and mathematics from Stanford and a PhD in physics from Caltech. His work has been featured in Nature, Nature Photonics, Science, Physical Review Letters, and has twice been on the cover of Scientific American. He was recently awarded one of the largest personal grants in Europe, a $2.5 million, you don't have it in dollars, is it euros or dollars? Dollars, okay, all right. To perform small-scale light sail launches. He's been an innovator in the semiconductor industry. Quick commercial. If you're interested in solar sails, the next International Solar Sailing Symposium, which I also am a committee member for, will be at Delft in the Netherlands in 2 years. So you might want to mark your calendars for that. The date is TBD, but Dr. Jeanette Heiligers is coordinating that. So it's my pleasure to turn over Dr. Norte.
Great. Yeah, thanks everyone. I really appreciate the invitation to come and give this talk. Especially with a lot of like-minded people who are interested in exploring. And I always like to start off this with this nice photograph of a shuttle launch, because I think it kind of, for me, captivates what gets us all here, right? We all want to figure out how to get off this rock and explore a little bit. But I like this little infographic because it gives you a sense of the kind of exploration that we've done over the last, 60-something years. We've made several missions to the moon. We've made several missions to Mars. Yes, many to Mercury. There we go. And if we go out to the outer planets, we start to get a few missions around Jupiter, Saturn, Uranus. But if we really look at the totality of the situation, like we all know, it would take really a long time. We're really very far from getting to Alpha Centauri even. Really 10,000 years, let's say. And so for me, in 2016, I saw the announcement of the Starshot Breakthrough Initiative. This was actually quite new to me, I have to say. But I was really inspired by the idea here. The idea being, of course, to make these large sails, make a gram scale probe, and really try to reach Alpha Centauri within a generation. I think it was a really nice and really compelling idea for me. So maybe just to get a sense of what that is, right? So the idea is that we want to make a microchip. We want to have all the sensors. We want to have the cameras, the communication systems on this chip. And then we want to attach it to a sail that is 4 by 4 meters and is 1 gram itself around. And just to remind everyone, a US penny is around 2.5 grams. So this is really something where it needs to be nanoscale thickness, more or less. That's where you end up being. And the idea is that with about 10 minutes of laser exposure, we can get up to these really large velocities. And one of the things that I want to say here is that I think for me, what really was compelling was the sail. What you'll find is that the sail is actually one of the really big challenges in this system, in this concept. And the reason being that if you look at the microchip, right, the idea is that we want to get the cameras to be as small as possible. We want to make the sensors as small as possible. But that's what we've been doing over the last 50 years. We've been making everything smaller in X, Y, and Z. Whereas the sail is a very special component because it needs to be nano thickness, but also expand out to really large scales. And that makes it very different from any other challenge, I would say, and very different from any kind of nanotechnology that we've tried to approach before. So this just gives you a sense, and this is kind of one of the things that I really feel about this is that, I think the how do we make everything smaller? That's something that goes in line with what we've been doing for the last half century. And I really think that a lot of the new breakthroughs are going to be in how do we combine large scale and small scale nanoscale components, really make something large in X and Y and make it small in Z. And that's not an easy thing, because you have to really start to think about how do you design this? How do you fabricate it in a way that scales well? Usually in nanotechnology, we make something smaller and it gets cheaper. Now we're making single components, which are very expensive, right? So this is really a big challenge. And I want to say that the field that I was working in before I saw this Starshot initiative was optomechanics. And this is something where they've really been thinking a lot about mechanics and optics already with these high aspect ratio structures. So the field that I worked in was cavity optomechanics, where you have two mirrors. One of the mirrors is movable, and you can make really very sensitive detection using this. This is what people have used to make some of the most sensitive measurements in science, I would say. So for instance, LIGO is a cavity optomechanics experiment. And one of the things that you suffer from is that you don't want, if you have some very sensitive system, and you have this outside noise, what you want to do is you want to make sure that noise doesn't come in and ruin your system. That's what we think about in cavity optomechanics. So how do you get this thermal noise from the outside to not go into your system and ruin your measurements? And so people have already thought about how to do that by making essentially 2D mirrors. So really a mirror made out of a single sheet of material, which is perforated with holes. And essentially what you find is that in this field that's already been working on this, making very, very thin mirrors, we already had many of the same requirements that, for instance, a mission like Starshot has, but for completely different reasons. We want zero absorption because that ruins our sensor measurements. It brings in noise. We want high aspect ratio so that we can be very untethered to the noise outside. So this is very, very interesting to me when I saw this announcement, because I thought, actually, we've been working on this problem, but at a very different scale. So how do you make a membrane, a 50 nanometer, 100 nanometer thick membrane into a mirror? Well, essentially, you grab this material and you puncture it with small nanoscale holes, which is kind of counterintuitive, but essentially you make it into a reflective metamaterial. So this is a little bit of a rendering of what that looks like. It's just a suspended film. We can make them into little trampolines like this and puncture them with holes to make them reflective. And just to show you that without the holes, you would probably get a reflection of about 30% across a wide bandwidth. But with the holes, we can really get a very high reflectivity at a very specific wavelength, which is perfect for lasers, which also operate at a single wavelength. And so the idea here is the light comes in, it creates a mode inside of this hole-filled membrane, and it constructively interferes with the incoming light and destructively interferes with the outgoing light. And so you basically have a mirror. And it's basically one of the thinnest mirrors you can make from a single material. Just to give you a sense, because there's always a sense of what is small, what is thin, right? So if you look at the solar sails like Icaros, that's really something that's on the order of about 7 microns thick. It's a polyamide layer with some metal reflective metal layer on top. And this gives you a little bit of a scale of what a photonic crystal looks like. It's really a single layer punctured with holes to make it reflective. And if we look at all the materials that people have used for making photonic crystals, silicon nitride ends up being kind of one of the best materials that actually covers all the needs that you have. We can make it big, we can make it reflective, we can make it without wrinkles. And it actually has parts per million absorption. So it has extremely low absorption, so we won't blow this thing up when we shine a laser on it. So this is just to give you a sense of what do these mirrors actually look like, right? So this is a scanning electron microscope of one of these silicon nitride membranes. If I zoom out a little bit more, this is what a membrane looks like. Everything in blue is a suspended membrane, and everything in purple is the little substrate that it's attached to. And if we zoom out even further, you can start to see how big So these are kind of the largest structures that were really being made at the time that I saw this Starshot initiative. And so I started working on this quite a bit and started trying to figure out, can we actually make these things bigger, and really started thinking about the physics of the manufacturing of how do we make this sail material. And so now we can, for instance, just to give you a bit of a scale, these are some arrows next to that one I just showed you, which was about 1/3 of a millimeter by 1/3 of a millimeter. And now we can start to make really centimeter scale photonic crystal reflectors. So this is really what you're looking at is really one of the highest aspect ratio nanophotonic structures ever built. And here, one of the neat things is that we've started to find that we can actually make a better reflector at these larger scales than we ever could at these very tiny scales. And the reason for that is that because now you can actually have a beam that interacts with, millions and millions of holes. So now we can actually expand our beam out. So one of the things we've been working on is how do we actually couple a laser with a sail, right? So there's been some groups that have been using, for instance, things like topology optimization to really try to figure out how to accelerate these things very fast. We've also been working on our own form of optimization that combines neural networks and also topology optimization. It's a PhD in my group who's sitting in the audience. And so one of the things we've been thinking about is how do we design these things better? And I think Philip brought up a really good point, which is the cost. The cost actually ends up being a really big point here because you're starting to make very large, big structures. If you look at the picture that I just showed you of that big giant membrane that I made, this thing costs about $25,000 just to write all the little tiny holes that are required for this thing, because they need to be small enough that we need to use an actual electron beam writer, which essentially writes bit hole by hole. So this took about 3 days with this expensive machine that's about 300 euros per hour. So that was really nice of Dell to do that. But one of the things is if we really think about what we want to do in this mission, the idea is to make a lot of sails and have a shotgun approach. You want to send out many of them, hoping that one of them will reach the target, right? So that means they need to be cheap. They need to be easy to make. And we also, for instance, want to work on things like the alignment resilience. We always assume that the laser is just going to hit this thing at a perfect angle and the perfect linear polarization, but that's also going to be very difficult. So can we design for these kind of things? And so, for instance, in nanophotonics, whenever you want to make a reflector, you generally have something like a square array of holes or a hexagonal array of holes. But one of the things that we started thinking about is, can we make the feature sizes bigger? So if the feature sizes get bigger, it means we can use other types of manufacturing that are much cheaper, that we can do at scale. But we will pay the price in terms of something else. Say it may not be as reflective, but it may be 10,000 times cheaper to make, let's say. So this is something that we started to do, and we started to find new designs that look kind of like Penrose kind of structures or pentagonal lattices. So it actually starts to get very interesting when you start to think about the cost. You start to see actual new designs in nanophotonics. So this is some of the designs that we got, for instance. And here you see the pink one is just a hexagonal lattice, just like I showed you before, where the reflectivity is very high at one point. But it also starts to find other designs where it's not as reflective at one point, but maybe it's actually kind of reflective over a large range. Because remember, these sails are going to be accelerating to large velocities, and you're going to have very big Doppler shifts. So it needs to be reflective over that whole range. So for instance, now the machine learning algorithm started to find that actually it might be better to have something that's not as reflective at one wavelength, but maybe spreads it out over this space. We also started to look at things like what if there's a little bit of misalignment in terms of the linear, you have a laser that's linearly polarized with your, and aligned with your sail? What if what if you have a little bit of misalignment? Can we have designs that, for instance, start to be very resilient to that misalignment? So you start to get really very interesting designs, and we start to look at things like, actually with, for instance, with this kind of pentagonal lattice structure, we can actually start to accelerate these things to this kind of v over c over 5 velocity much quicker than we could with other designs. And so so this is just thinking about the unit cell, but we're also starting to think about really realistically, how do we design the entire sail, the long range design of this reflective sail. And this is work that we've really been working on a lot, been supported by the Limitless Space Institute. So we're really happy about where this is going right now. And so now we're really trying to make these structures. So I think, this is my feeling, just kind of given nanotechnology today, I think meter-scaled light sails are a long distance away. To be very realistic, it's a very long distance away considering what we can do with nanotechnology today. I think it's still some decades. So the question is, what can we do today? What is actually possible with the extent of nanotechnology possible today? So these are all the wafers that have been made since, how wafer sizes have progressed over the last decades. Here you had a 100 millimeter wafer, which I was holding in the last pictures. But now we can make them up to 450 millimeters large. So the idea was, if I made a sail this big, just given the extent of how large we can make silicon wafers, how long would it take me to get to Alpha Centauri? And now you start looking at numbers like 800 years. Maybe we can get it down to 200 years with the largest wafers available today. And this is assuming very conservative numbers. We're still taking 1 gram payload, and we have about 70% reflectivity when we can usually get 99%. All right. One thing that I found very interesting is that when you start to look at closer things, like how long would it take us to get to Voyager, let's say, and then the picture starts to get very interesting, because now you look at this 100 millimeter wafer, and we can start to get there in 162 days. And we can even start to think about, with these larger wafers, maybe even getting out to Voyager's position in 38 days rather than, the 47 years that it's been going so far. So I found that really very interesting, that the scales really change in that sense. And if you even look at the little, the demonstrator that I showed you earlier, we would be able to get out to Voyager's position in about a year, which I found really pretty cool. Because that's something we can actually make today. We have a photograph of it. So it definitely begs the question of, why not our solar system? Why don't we look at it much closer? Because if, for instance, if I look at just the fastest flyby probes in the solar in our solar system, you're looking at Cassini 7 years, Mariner 7 for 4.2 months. And we can really start just with the demonstrator that I showed you, right? This 4.5 centimeter by 4.5 centimeter thing. We're not accelerating it to very fast speeds, because obviously we have a smaller sail, so you can't accelerate it as fast. But you can already start to see these very drastic drops in the travel time. So for instance, we could get a 1 gram payload to Mars in, let's say, 32 hours. Or for instance, to Saturn in, let's say, 22 days. So I find that very compelling, the idea of just being able to send, microchips to Mars the way we send international mail, just shotgunning them in 32 hours. I think that's pretty cool. Or sending something to Titan's oceans in less than a month. So I think this is very, very interesting, given what is possible in nanotechnology today. So what do we want to do in our lab is, we've made these things. You notice that I can actually take a picture of it. I can hold this sail and nothing happens to it. It's a pretty stable thing. But what if we start making things that are just not possible for me to handle? Something that's really untethered, that you can really start to lift with coherent optical light. and maybe even carry some kind of payload with it, some kind of silicon payload. So this is something that we've now been thinking a lot about. So as mentioned, we recently got a lot of funding from the EU in order to actually pursue this. This has actually been a lot with the support from the Limitless Space Institute, has kind of kept the project going and allowed us to then apply for this. So that's been really great. So the idea here is that what we want to do is, normally what we do is we fabricate a sail, and then we take that sail and we very, very carefully take it over to an optics lab and hope that not a speck of dust falls on it, and then put a high-powered laser on it. That would be the idea. What we're doing is we're saying, I think we need to combine the fabrication and the actual lifting with the sail at the same time. So what we want to do is a small-scale launch on Earth, where we actually fabricate the sail in a plasma etcher, and we've essentially made a custom plasma etcher that allows us to remove the silicon underneath, suspend the structure, move it carefully without breaking vacuum, and then use a high-powered laser to try to lift the structure up. And so here the idea is really to lift the structure against gravity. And the other thing is to try to, basically what you can think about is, you can think about a rocket that you've tied down, and just to figure out what all the dynamics look like, you just start launching this thing and trying to see what the dynamics look like. And one of the things we also want to do is we want to be able to move the laser to say that this thing actually rides the beam. So we move it this way and it doesn't go. One of the major challenges is that you have your beam on your sail, and you want that even if it veers off, it veers back into the beam passively. So we also want to try to demonstrate this kind of stability. So just to give you a sense, right now with optical levitation, the biggest thing that people have done in optical levitation has been something on the order of 10 nanograms, something like that. People have been using these kind of optical levitation to make extremely good sensors, which are essentially completely isolated from outside and noisy environments. And what we want to do is something like this. There's also already been proposals to essentially lift milligram scale mirrors with these kind of tripod proposals. And what we want to do is something where we really start to take a sail and start to nano pattern it and try to lift it up. And what we're talking about here is really trying to lift something that's milligram scale. So that's really something almost 100,000 times larger than anything that's been levitated with coherent light, to date. So these are kind of some of the main things here. We think there's going to be a lot of novel light matter interactions. The self-stabilized metamaterials is going to be something that's going to be a real challenge. How do you not just make the same hole over the entire sail, but how do you slowly change it so that you actually have a self-stabilized structure? That's not a very easy design question. So we really think here that we're going to really have some new interactions with really new material science and photonics applications. We're going to be looking at really new levels of optical levitation, structural engineering. When you have these kind of massive objects, which are really just balancing the delicate balance between coherent light and gravity, you're going to start to get some very interesting sensors. Because then now you have essentially a large mirrored system, which is completely mechanically isolated from outside environments. And light is actually very good. It's very mechanically not lossy. And we've also been now looking at how to actually look at new materials for this. So now we've, for instance, been discovering new materials which have extremely high yield strengths, something kind of now approaching the levels that we can get with graphene. So that's actually pretty neat. And maybe one of the things I wanted to say here is that I think in this post-Moore world, the Moore's law is going to be ending in almost 2 years. And I do think that the light sails represent a new type of technology that's gonna kind of go post-Moore. I do think we need new types of optimization to design, not just at the small scale, but design these really large structures that have also nanoscale features. It's a very weird combination of things. I think the small scale launch is going to be really important. towards these technologies. And I think that we can already do some very interesting things in the solar system. So I think the prerequisites for interstellar travel are also very interesting. And I just want to give a big thanks to the team. A lot of our supporters, and thanks for your attention.
An excellent presentation, and as a solar sailor, I learned a lot, and I have a lot of questions. So I'll wait and catch you in the hallway. So let's open it up for in here, and we'll start on this side.
This may have been on your slides, if so I apologize. Is your mission profiles of a couple days to Mars and a couple of weeks to Saturn, are you keeping the sail in the beam the entire time, or are you giving it a kick right outside of Earth orbit and letting it coast?
The latter.
Okay, thanks.
Yeah. At least that's how I imagine it. I think it's going to be a combination of talking to the laser guys here and figuring out how to do it. But yeah.
Hello. First of all, excellent presentation. This might be more of a question for your PhD student, but how exactly does the topology affect the reflectivity? And like for your topological optimizations, what are you actually doing if it's not just like changing the distribution of the holes?
Sorry, so the question was,
how does the topology affect the reflectivity of the membrane?
You mean the topology of the like, you mean the
like the lattice of holes?
Oh, the lattice of holes. So you can basically tune the size of them and the spacing between them to reflect at whatever a wavelength you want. It seems just from what is cheaper in the laser community, 1064 is going to be what we have to go towards. Although we would love if the high-powered lasers were at a larger wavelengths, because then it means all the holes and all the features are bigger, which means cheaper to make. But I think the money for the lasers is probably our real limit now. So we're gonna go with what the laser community's dictated in a way.
Good, thank you.
Yeah. Hi. Hey, Richard.
Yeah.
You mentioned that you think the meter scale sails are, maybe decades away, which might be fine. You'll have to talk to Phil about how long it's going to take us to get the big laser. But do you think that time scale is because there are just really hard technological challenges, or is it because there isn't a use case other than solar sails or light sails for this kind of technology?
The reason I say it is only because if I look at this, and I did the calculation one day, just looking at this progression of how big wafers have gotten, and this is with all the motivation of Moore's law and the billions of dollars in microchips. If I look at the rate at which this is growing, and if there was a real use case for going to a meter scale thing, this would take. I think we'd get to meter scale in about 100 years. That was the kind of the rough. If I took this rate.
Scale sails at the moment for meter scale wafers?
I don't think so. Yeah. I think it's starting to get more and more difficult.
And can I just ask one more question? Do you have an opinion on stitching together smaller size wafers?
Yeah, I've gotten that question a lot about how if you can just put together wafers or maybe put together sheets or sails. But I have to remind everyone that when you're talking about 100 nanometer thick thing, you're talking about, usually if you look at a bubble that my child likes, it's usually around the same. So it's basically making a giant bubble, and then how do we stitch this bubble together? And this bubble also is not a continuous film, but it's completely covered, Swiss cheesed in little nanoscale holes. It's a very difficult material. Like when you really work with this material, you start to see how fragile it is. But that's why I think this whole beam alignment and how you couple the light to this very fragile thing, it can do amazing stuff if it's interacted with in a uniform, correct way. You know what I mean? So it's fragile but powerful if you interact with it in the right way.
We have time for one more question.
I'm curious, for these holes, do they have to be through holes, or can you do something like blind holes, given that, eventually you may want to put actual MEMS, on the sail. So you need somewhere to mount them.
The question is, do you want MEMS on your sail? That's where the high-powered laser is going to be pointed at. And the other thing is that it's actually a really nice thing that you can put holes into something and make it more reflective, because then you get rid of mass. So we almost get rid of half the mass of the sail.
Gotcha. I guess I was curious, like, do the holes have to go all the way through, or can you make like blind holes and still get the same effect of the reflectivity?
It'll just be a worse effect. But at the end of the day, it's kind of nice to have through holes, because then if there's interstellar dust or whatever, as long as it's smaller than that, maybe it'll actually help for survival. So
Makes sense. Thank you.
yeah.
Thank you again.